Hi class, today we're going to be talking about functions and giving you the basics for introducing what a function is. Our linear equations are actually one type of function that we're going to be dealing with, and we'll need to be able to use our regular notation for our linear functions and then also function notation for them. So in order to know what a function is, we first need to know what a relation is. And a relation is when you have two values that relate in some way. Now, relations can sometimes be listed as sets of ordered pairs. So you might have a set of ordered pairs where you have 2 matching up with 4, and maybe it also matches up with 5, and then you have 3 matching up with 6. And this is a relation where you have some values that if for some reason relate to each other. The 2 relates to the 4, and then another 2 relates to a 5, and then 3 relates to the 6. You also may have another relation where maybe 1 maps up to 2, and then you have a 2 that's going to a 3, and then a 3 that's mapping up to a 4. Now, you can see these two situations listed as ordered pairs like you see here, or another way to look at them is to have a mapping. Now, each of these values here that would be our x-coordinates if we were graphing these points are called input values. So for this first situation, if we wanted to list the values that are what we call inputs, the only thing that is an input is either a 2 or a 3 in this situation. These input values are your x values or x coordinates, and they are also what we call our independent variables, and they're also what we call our domain. The output values, I'm going to put in this oval here. They are your y coordinates. They are also what we call the range. Now, range starts with R and domain starts with D. If you look at the alphabet, D is before R in the alphabet. And if you look at X and Y, X is before Y in the alphabet. So one way to remember which is that X goes with D because they're first in the alphabet, so the X coordinates are the domain. Y goes with R because they are the second things in the alphabet, so the Y coordinates are the range. Now, if we look at the y coordinates for this particular relation, we have a 4, a 5, and a 6. So I'm going to put a 4, a 5, and a 6 in this. This way I'm going to show you to look at this same relation here using these ovals and some arrows to map the inputs to the outputs is called a mapping. Now, since the 2 matches up with a 4, I draw an arrow from 2 to 4. Since it also maps to 5, I draw an arrow from 2 to 5. And then 3 maps to 6, so I draw an arrow from 3 to 6. And that's the mapping for our first set of values. Now, let's look at the mapping for our second set. The domain, which is the x values, is a 1, a 2, or a 3. So we list those numbers in this first oval. The range is the y values, and those are either a 2, a 3, or a 4. So we'll list those in the second oval. If you look at your first ordered pair here, 1 matches up to 2. And then the second ordered pair, the 2 matches up to the 3. And the third ordered pair, the 3 matches up to the 4. So now we've looked at these two relations here and how they would look like if they were sets of ordered pairs here or a mapping as we see in these two spots. Now, these two relations are both relations, but one of them is what we call a function and one of them is not. So let's look at what a function is. A function is a relation where every input value, which is also called the independent value, has only one output value, which is the dependent value. The input value is independent because you can plug normally almost anything in that you want, but what you get out will depend on what was plugged in, so that's why we call the output a dependent value. So we want every input to have only one output. Well, if you look at your sets, that means you need to make sure that in your sets, the x values only show up once. Because if they show up twice with different outputs, like in this case you have 2 and 2, and they come with two outputs, a 4 and a 5, if that happens, then you know that it's not a relation, or the relation is not a function. Now, if you look at that same set as a mapping, like we have over here, notice that the 2 has more than one arrow coming out of it. That's another clue to you that this relation is not a function because you only want one arrow coming out of it. If we look at the other relation, notice that each x value or input value, which is the independent value, only shows up once, which means they only have one output value or dependent value. If we look at the mapping here, we only have one arrow coming out of each value from the domain. So that means that this is a function. Now in real life, there's lots of things that will end up being functions and things that will not be functions. For instance, if you go to buy a car, oftentimes if you go to different dealerships, you could have the same exact car, same color, same options, but depending on the deal you're able to negotiate, you could pay different prices for that same exact car. That means that that situation is not what we would consider a function. However, there are certain things that you purchase that the manufacturer has done what's called a price fix on. For instance, Bose speakers had, at least at one time, been price fixed so that no matter where you went to buy them, you would pay the exact same price. So the only difference between buying them from one place and a different place would be the customer service, and if you liked that company. But as far as price goes, you were going to pay the same price, and Bose wanted it that way. And if they sold it for a different price, Bose could pull their ability to sell those kind of speakers. So that particular situation where a manufacturer has done a price fix on an item is a function because no matter where you go, you are going to pay the same exact price for that item. So those are some kind of things that could be in real life that would be functions or would not be functions. Now, these two situations that we've looked at so far, we looked at them being represented as a set or as a mapping. We can also look at things graphed on a coordinate plane. So let's take a look at what that would look like. If we have a coordinate plane, our x values here, which are on your x-axis, are going to be what we call our inputs, and those are also going to be what are our domains. The output values are your y values, which will be found off of your y-axis. That's going to be your outputs, which is also your range. Now, if you have some kind of function that's graphed on here, there is a test you can do to find out if it is a function. If every time you go across this x-axis and choose a value, that when you go up to wherever the graph is, there will be only one y value that matches up with it for the point on the graph. Let's pretend that you have a shape that looks like this. this angles out like that. If we do what's called the vertical line test on this graph, everywhere on this graph, if we draw a vertical line, no matter where I choose to draw that vertical line, it will cross my graph of my item at only one point. Because of that, we would say that this particular graph of this particular situation passes the vertical line test, and so this is a function. So what I just did there by basically trying to draw a whole bunch of vertical lines to see if it only passed through one point was called the vertical line test. And if it passes the vertical line test and only goes through one point, as you see here in each of these situations, then you say that it is a function. Now you might have a graph of another situation, something that actually does have an equation, but it doesn't pass the vertical line test. For instance, if you continue on in math and you learn about equations of what we call an ellipse, which will look like this, you'll find that this actually does have an equation that involves x's and y's. However, if you try to do the vertical line test, it has multiple places where it will cross more than one point. So even though this ellipse does have an equation, it does not pass the vertical line test, so you would say that it is not a function. Now that's how you know if something is or is not a function. Let's take a look at the notation for functions. When you have a function, there's a notation that's often used where you have some letter. F is used a lot because the word function starts with F. And then you have parentheses and you have some variable inside. We use x a lot because x is the independent variable on the coordinate plane for your x-axis. However, if you have a situation where the function is talking about cost, and it's cost based on how many things that you are building, you might use C instead of F because cost starts with C, and you might use N instead of X because number of items starts with N. So you might have different letters, but basically you're going to deal with them the same way. If something's population, you might use P for the name of the function, and then maybe it's population based on years. You might have Y for years. So you can use any letters that you want, but basically you want to remember that this thing right here is actually a name of a function, and it's the name of the function is f, and we are plugging into the function the variable x. So this is not f times x. In fact, when we say what this here is, you say f of x. And that's meaning the function f, you're plugging x into it. So let's take a look at a situation where we have the function notation. Maybe we say that f of x equals x squared minus 3x. And maybe you're told to find f of 2. What that means is to take this function right here and plug 2 in wherever you see x and just calculate out the answer. So what you have here is f of 2 will equal, replace this x with 2, which will be like that, and replace this x with 2, which will be like that, and then just calculate it out. So order of operations has us square this to get 4. Then we multiply this to get 6. And when you subtract those, f of 2 is negative 2. You are completely done calculating at that time. A lot of people at this time will want to divide both sides by 2, but you don't want to divide by 2 because you were trying to find out what f of 2 was, which means just plug 2 in and calculate. You're not finding what f is because f is the name of that function. So now this particular sentence here means that when you plug in 2, you get negative 2 back out. You can actually write that as an ordered pair where you plug in 2 and you get negative 2 out. This corresponds to a point on a graph. The point on the graph is going to have an x-coordinate that is 2, and then the y-coordinate is really your value you get after you calculate f of x. So you can think of the y value as being similar to your value for whatever f is once you plug in that variable x. And in this case, the y value is negative 2. Now, let's take a look at one more problem where we're finding something using this equation. Let's say you're told to find f of negative 3. That means we want to plug in negative 3 wherever we see the x. So we're going to plug it in right here. Now, a common mistake when you're plugging a negative number in and you're squaring it is that people will not put parentheses around here. So they won't actually square the entire negative 3. They'll just square the 3. So you want to be careful that when you plug the value into your formula, you always put parentheses around it to prevent that mistake. So now, if we square negative 3, that's negative 3 times negative 3, which is a positive 9. Then multiplying this, you have negative 3 times negative 3, which is positive 9. And when you combine those, the value for f of negative 3 is 18. If we were going to be plotting this on a coordinate plane, that would correspond to the point negative 3, 18. Now, let's relate this to our linear equations. You might have an equation that's y equals 2/3 x minus 1. Instead of writing it like this y may not end up being a y. It might end up being f of x. This is asking you to do the same exact thing as what I had written just before. If you were going to graph, you would actually make a table, just like you would if the f of x was a y. And in your table, you would have your x values here, and you would have your y values here, which in this case are really not your y values. They're f of x values. That means you're going to take these x values here, plug them into this formula, and calculate and write down what you get for an answer. And then when you write your ordered pairs, you'll have your x-coordinate as the first coordinate, and your y-coordinate will be the value you got after plugging x into f. So let's do that for this equation. Let's find 3 points, 3, plugging in negative 3, 0, and 3. Notice that I chose values where this 3 in the denominator of my slope will cancel. So now I'm going to go ahead and calculate. I need to calculate f of negative 3. That's going to be 2/3 times negative 3 minus 1. Notice that 3 goes into negative 3 negative 1 time. If we multiply 2 and negative 1, I get negative 2. When I subtract 1, I get negative 3. So this is negative 3, which gives me the point on the coordinate plane that corresponds to negative 3, negative 3. Now, if I go ahead and plug in 0, I am going to get f of 0 equals 2/3 times 0 minus 1. And 2/3 times 0, it just turns into 0. So that means f of 0 is negative 1. So this is negative 1, which will correspond to the point 0, negative 1. Now let's go ahead and calculate out for our third point, which will be f of 3 being 2/3 times 3 minus 1. Notice the 3's will cancel, and I end up with 2 minus 1, which is 1. So that is 1, which corresponds to a point at 3, 1. Now, if we want to completely graph this function, all we need to do is make a coordinate plane and plot our points and then connect them. And you'll see that we get a line just like we did when we were dealing with graphing lines using tables. So let's go ahead and label our coordinate plane. We'll put a few values on here to know our scale. And then plotting our first point that we found here is -3, -3. So we go to -3 on the x, then -3 on the y, and we'll plot it right there. Now, our second point here is 0, -1, which is going to be right there. And then our third point, which helps check to see that the first two were in the right spot, is 3, 1, which is going to be right here. Now all we have to do is connect those. And I'm going to actually have to move this for down. And if we're to scale, which I'm not completely, you would see that that is our line and they all line up nicely. So that's how you would go ahead and graph a linear function written in function notation.